Big ideas? Short lessons.
Imagine a tall pile of cafeteria trays. You can place a clean tray on top and you can take the top tray away, but reaching into the middle would disturb everything above it. A stack is a data structure that deliberately keeps this rule. We add and remove at one end, called the top. That may sound limiting, but the limit creates order. The newest tray is handled first, without searching through the pile or shifting every tray. Computers use the same idea when the most recent unfinished thing should be the next thing completed. So a stack is not just a pile. It is a promise. Work with the top, and the order will take care of itself. Let's label 3 trays. Amma goes in first, then Ben, then Chen. Chen is now on top. If we remove trays, Chen leaves first, then Ben, then Amma. Computer scientists call this last in, first out, or LIFO. It means the last item added is the first item removed. The bottom remembers the oldest item, the top exposes the newest. Notice that LIFO is not a sorting rule. The stack does not compare names, sizes, or importance. It remembers only arrival order. Once you know which end is the top, you can predict every result. New items enter there. Available items leave there. Everything below simply waits. Adding an item to a stack is called push. If the stack contains Amma and Ben, pushing Chen places Chen above Ben and makes Chen the new top. We do not search for position, compare values, or move the older items. We only update the end we already know. In an array-backed stack, top can be the final occupied index. In a linked stack, top can be a reference to the first node. The storage looks different, but the promise is identical. Push changes 2 facts. The new item joins the stack, and top now identifies it. That tiny local change is why push is normally constant time. To remove the top item, we pop. With Amma, Ben, and Chen stacked in that order, pop returns Chen and removes it. Ben becomes the new top. Sometimes we only want to inspect Chen without changing anything. That operation is called peek, and some languages call it top. Peek answers, what is available next? Pop answers the same question and then consumes the answer. That difference matters. An undo button may peek to show the next action that can be reversed. Then pop only when the user confirms. Both operations touch a location we already know, so both are normally constant time. The stack never needs to scan its contents. Why are push, pop, and peek so fast? Not because stacks are magical, but because they refuse a harder question. Ask for the top of a stack containing 3 items or 3 million items, and the answer is still at the known end. One direct change gives constant time work, written O of 1. But ask to remove the bottom tray, and the stack cannot obey without moving past everything above it or exposing an operation outside its contract. The restriction is the optimization. A stack gives up arbitrary access, so the newest item stays cheap to reach. If your program constantly needs the middle, a stack is probably the wrong structure. What happens when there is no top item? Popping or peeking an empty stack is called underflow. A careful program checks whether the stack is empty or handles the language's empty result before using it. You may also hear overflow, trying to push when no more capacity is available. Overflow applies naturally to a fixed size stack, like a tray holder with room for exactly 20 trays. A dynamically growing array or linked implementation may expand instead, until the computer itself runs out of memory. So empty is universal, but full depends on the implementation. Good stack code makes both boundaries explicit instead of assuming an item is always waiting. A stack describes behavior, not one required shape in memory. We can build it on an array. The final occupied position becomes the top, storage is compact, and computers usually read nearby memory efficiently. Push is constant time on average, although growing a full dynamic array occasionally copies the items, or we can build the stack with linked nodes. The head becomes the top, so push and pop reconnect only that first link, without resizing an array. The trade-off is extra memory for links and less predictable memory layout. Same push, pop, and peek. Different machinery underneath. This is why a stack is called an abstract data type. The rule matters more than the container used to keep it. Stacks appear whenever the newest unfinished step must resume first. Undo history pushes each new change, then pops the latest one when you press undo. A redo feature usually keeps a second stack for actions that were undone. Browser navigation can use the same 2-stack idea for back and forward. Depth-first search and maze-solving push possible paths, then pop the newest choice when they reach a dead end. Expression evaluators and parsers keep operators or opening symbols until the correct closing moment arrives. These jobs look different, but their hidden sentence is the same. Remember what I just left unfinished, because I will need it before the older work. Let's examine the 2 examples that make this pattern impossible to forget. Suppose main calls make breakfast and make breakfast calls toast bread. Each call gets a stack frame. a small record containing that function's local data, its arguments, and where execution should return. Main's frame is pushed first, make breakfast goes above it, and toast bread becomes the top. Toast bread finishes first, so its frame pops and the program resumes inside make breakfast. Then make breakfast pops and main resumes. Recursion uses the same mechanism. A function calls itself, pushing a new frame each time. A base case eventually stops the calls so the frames can pop in reverse. Without a reachable base case, frames keep accumulating until the runtime cannot add another. That error is a call stack overflow. It is not the same as popping an empty stack. It means the real bounded call stack has run out of room. Now let's solve a real problem. Is the expression parentheses, square bracket, curly bracket, square bracket, parentheses correctly balanced? Read from left to right. Every opening symbol is unfinished work, so push it. When a closing symbol arrives, the stack must not be empty. Pop the newest opening symbol and check that the pair matches. The closing curly bracket pops the opening curly bracket. The closing square bracket then pops the opening square bracket. The final parenthesis pops the opening parenthesis. At the end, the stack is empty, so the expression is valid. There are two failure rules: a closing symbol with no opener or a closing symbol that does not match the top. And even if every comparison passed, leftover openers at the end also mean invalid. A stack fits because nested things close from the inside out. The newest opening must close first. In JavaScript, an array can act as a stack. Push adds to the end, pop removes from the end, and the final index lets us peek. In Python, a list does the same job. Append pushes, pop removes, and index -1 peeks at the final item. Start with Amr and Ben. Push Chen. Peek returns Chen, but the stack stays unchanged. Pop returns Chen, and Ben becomes top again. The syntax differs, yet the state changes are identical. One warning: empty behavior differs. JavaScript pop returns undefined, while Python pop raises an error. Check the length before using the result. Also avoid removing from index 0 when you mean stack behavior. That chooses the opposite end and may shift every remaining element. Learn the rule first, then the library method names become easy to remember. Here is the complete performance picture. Push is O of 1 for a linked stack and amortized O of 1 for a dynamic array. Pop and peek are O of 1. Searching is O of n because the stack may need to inspect every item, and arbitrary indexed access is not part of the stack contract. Storing n items requires O of n space. Now ask the decision question: should the newest item be handled next? If yes, a stack is a strong candidate. If the oldest arrival should go next, choose a queue. If you need fast access to any numbered position, choose an index structure. Remember the tray pile: push adds at the top, peek reads the top, pop removes the top, and LIFO means last in, first out. The top-only rule is not a weakness. It is why the structure is predictable and fast. Next, we turn the pile into a line and learn queues.